Good morning, all. Welcome to another session of Fluid Mechanics. This is Professor Prakash, Assistant Professor, Department of Mechanical Engineering, Saga Institute, Bhopal. Today, we are going to discuss about Pascal law. Pascal law states that a change in pressure applied to an enclosed fluid or a confined fluid is distributed or transmitted evenly throughout the fluid in all directions. In simpler terms, this law implies that when you apply pressure to a confined fluid, the pressure is transmitted equally in all directions throughout the fluid and against the wall of container. Or we can also say that pressure or intensity of pressure at a point in static fluid is equal in all directions. The Pascal law applies to the fluid that are enclosed within a container, whether it's a liquid like water or a gas like air. The key is that the fluid cannot escape its confine. Regardless of shape of container or where the pressure is applied, the Pascal law asserts that the pressure change will be transmitted uniformly through the fluid to the walls of container. It is also known as Pascal's principle or principle of transmission of fluid Pascal. For example, let us imagine you have a closed container filled with water or any other fluid. If you apply pressure at any point within this container, say by pushing down a piston, Pascal laws state that the change will be distributed evenly throughout. For example, let us say we have a container and have two pistons, piston A and piston B, and we have a fluid confined in this container. Now, when I apply a force or a pressure on piston B, the same amount of force will be transmitted to piston A. This occurs because the fluids are nearly incompressible, meaning they resist the changing volume when the pressure is applied. When the pressure is applied, this is how the hydraulic systems work. So, if we consider the applications of the Pascal law, then the hydraulic systems are the most common applications of the Pascal law. For example, the hydraulic lift, the image that we saw in the previous slide, is a simple line diagram of a hydraulic lift. And this hydraulic lift, we apply the force on one side, and on the another side, the weight gets lifted up. It can be a car, it can be some heavy machine, or it can be a simple lift. The construction is such that a narrow cylinder is connected to a wide cylinder. They are fitted to airtight piston on either end, and the inside is filled with a fluid that cannot be compressed or that is incompressible. So pressure applied on one cylinder is transmitted equally to another without diminution. Few more applications include hydraulic press, hydraulic braking system, heavy machinery, excavator, crane, and medical application, such as in medical application, Pascal law is employed in devices such as blood pressure curves and syringe. Blood pressure curves measure the pressure by applying pressure to the arm, which is then transmitted to the enclosed fluid and detected by the pressure gauge. The syringe uses the Pascal's law to deliver precise dose of medication by exerting the pressure on the fluid within them. And moreover, we have pneumatic systems like air brake or pneumatic tool, which also work on the Pascal's law. So we can see the Pascal law is a fundamental concept in fluid with numerous practical application across various day-to-day life. Now, A law is made when it can be proved mathematically. So let us prove the Pascal's law mathematically. So to prove it mathematically, we will consider a fluid of dimension dx, dy, and ds having a thickness of unity. That means its volume will be dx, dy, ds. And let this be a wedge-shaped element. So it will be simpler for our analysis. So in this wedge-shaped element ABC, the face AB is having the dimension dy, AC is having the dimension dx, and BC having the dimension ds. And the angle ABC is angle theta. Now, let us firstly determine the forces that are going to act on this fluid element. So, on the face AC, there will be a pressure force. On AB also, there will be a pressure force, and on BC also, there will be a pressure force. If you remember, the pressure force can be calculated by multiplying the intensity of pressure with the cross-sectional area. So, on the face AC, the pressure force, let the intensity of pressure is Py in the y direction. Then the pressure force will be Py into Py dx into 1. 1 is the width. On the face AB, the pressure force will be Px dy into 1. And on the side BC, the pressure force will be Pz ds into 1. Now, what we do in case of derivation is we resolve all the forces in vertical and horizontal direction and put the condition of equilibrium. That is, the forces must be equal in horizontal and vertical direction. But here we can see this pressure force is in inclined direction. So we will resolve the force with the help of this angle theta. So on resolving this force and equating in horizontal direction, we can have in x direction, we will have the equation px dy1 minus pz ds1 sine of 90 minus theta, which is px dy1 minus pz ds cos theta or pz ds cos theta. Now, what is this ds cos theta? So, if we go back to our figure and determine this, ds cos theta is nothing but it is equal to ds cos theta is nothing but this is equal to dy. It is simply that we are applying the principle of sine, cos, and tan. Okay, so by replacing ds cos theta by dy, we get px dy1 minus pz dy1 equal to 0 or px equal to pz. This is our first equation. Now, doing the same thing in y direction, in y direction calculation, we will have py dx1 minus pz ds cos 90 minus theta minus dx dy by 2 multiplied by 1 multiplied by rho into g. What is this? This is actually the weight of fluid element. The weight of fluid element can be calculated by multiplying density into g into volume of element. So, in this rho is the density of our fluid element, g is acceleration due to gravity, and this is the volume. Volume half base into height, that is half dx into dy multiplied by the width 1. This is the volume. Now, since the element is very small, We have considered a very small fluid element, so we can say that the weight is negligible. And like ds cos theta was equal to dy, we have ds sine theta equal to dx. Therefore, by putting these, we have py dx minus pz dx equal to 0 or py equal to pz. By combining both the equation, we have px equal to py equal to pz. This equation states that the pressure at any point in x, y, and z direction is equal. This law is valid. This is the derivation of Pascal law, and it is valid for the cases of fluid flow where shear stress do not exist. That is, the fluid is at rest. There is no relative motion between the different fluid layers. For example, fluid is at constant linear acceleration, and ideal fluid flow conditions are there. That means the viscous forces or viscosity is negligible. So, in conclusion, we can say that Pascal's law is a fundamental concept having numerous applications, whether it's stopping a car with the help of hydraulic brake, lifting heavy object with the help of hydraulic lift, or delivering medication by measuring the blood pressure. Pascal's law continue to shape our modern world, and understanding this law will help us to design innovative systems and devices to harness the power of fluid efficiently and reliably. So on this say, we conclude our session. Thank you. Sejanandam.